Hi everyone. In this session I will be looking at random variables, but specifically discrete random variables, and I will be looking at a few concepts regarding discrete random variables, and then in the next session there will be some examples. Now, up to this point we have looked at sampling and types of data, graphical summaries, numerical summaries, probability and conditioning, and counting techniques, and all of these combine when we start looking at random variables and special distributions thereafter. Now, first thing, as usual, will be the outcomes. Most important, you have to know the definitions. Secondly, you have to identify the link between a sample space and a random variable. So the sample space, which is the capital S or capital omega that we encountered earlier. You must be able to construct a PMF or CDF table or chart from word problems. You must be able to use the PMF or CDF tables and charts to calculate probabilities. You must be able to calculate the parameters, and you must be able to solve problems containing linear transformations of random variables. Now, you should be wondering, what is a PMF and what is a CDF? We'll get to those definitions in this session. Right now, the very first definition that we encounter is the one for a random variable. Now, looking at this definition, it seems very abstract, but all that it means is that x is a function that assigns a real number to the outcomes in the sample space. So in other words, x is a function that takes outcomes in the sample space and maps it onto the real line. So it assigns a real value to those outcomes. Now we'll see in a moment why that is important. Now, a random variable also refers to a population. So when we talk about a random variable, it will not be a sample. And then lastly, I will be looking at discrete random variables, which means that the number of outcomes that we work with will be countable. Doesn't matter if there are infinitely many outcomes, we are still able to count them. Now let's look at an example. First of all, consider flipping a coin 3 times. Now we have seen this before. First flip, we can get either a head or a tail. Same with the second flip, same with the third flip. And our sample space will simply be the combination of 3 components. So for the first branch, we have 3 heads, right? 1, 2, 3 heads. We combine them in to form our first outcome. Then if we take the first branch, we have 2 heads and then go down to a tail, then we have the second outcome in our sample space. Now, if we say that this is a fair coin, then regarding the probabilities, it will mean that each and every outcome here has a chance of a half of occurring. So a fair coin, 50% chance of getting a head, 50% chance of getting a tail. And it's the same coin being flipped 3 times, so all the probabilities will stay the same. Now, we wish to calculate the probabilities for these outcomes in the sample space. And the way that we do that is by using the multiplication rule for probability. We saw this in an earlier session, and it simply means that we multiply all the probabilities on every single branch. So these little red crosses here, they just mean multiply. So if I consider the first branch, then a half times a half times a half will give us the probability of 1 over 8 for getting 3 heads in a row. If we do that for the next branch, which will be half times a half, the blue ones, and then a green half, then that will be 2 heads and a tail. It will also be 1 over 8, because 1 over 2 times 1 over 2 times 1 over 2 is 1 over 8. And we do that for all the others as well. If we take the third and the fourth branches, we also just have a half throughout. If we look at branches 5 and 6, it's the same, and 7 and 8, it's the same. So now we have our sample space where we have all the outcomes listed, and then we have all the probabilities for those outcomes. Now we've looked at properties of these probabilities, and we see that the first property is that a probability can't be less than 0, it can't be greater than 1, because it's a fraction. We're counting how many outcomes we have out of a sample space. So the numerator will always be less than or equal to the denominator. So this ratio will always be, or this fraction will always be anything from 0 to 1. And when we add them all up, we must get a total of 1, because that represents everything in the sample space. Now, as this table is presented here, we cannot perform any calculations with the sample space because we don't have numbers. We simply have sequences of outcomes. 3 heads, 2 heads and a tail, head, tail, head, etc. So what we'll do is we will define a value x, and we'll say let x be the number of tails in our sample space for every single outcome. So that means the smallest possible value that x can be is 0, because there's one outcome here that contains 3 heads, in other words, 0 tails. If we look at the next 3 outcomes, each one contains 1 tail. So that means that another value for x will be 1. If we look at the next 3 outcomes, then we see that each outcome here contains 2 tails. So that means that another possible value for x will be 2. And then lastly, x can be 3 tails. So that means x will be equal to 0, 1, 2, or 3. Now we can actually find the probabilities for x as well. In other words, what are the chances of getting 0 tails when you flip a coin 3 times, or getting 1 tail, or 2, or 3? We simply look at the probabilities associated with the outcomes in the sample space, and we assign these probabilities to our random variable. So the first one, 0 tails, will have probability 1 over 8. The next one has 3 1 over 8s, and we combine those, and that will give us 3 over 8. So 3 over 8 is the probability of getting 1 tail. The same for getting 2 tails. There's 3 outcomes, each one 1 over 8. And then the last one, getting 3 tails, there is one way of that happening. So the probability will only be 1 over 8. Right, so what we have here now is our random variable that we derived from our sample space. So the sample space did not contain any numbers as outcomes, the random variable does, but only after we defined what our random variable represents. In this case, the number of tails. If somebody is interested in the number of heads, then they will say let x be the number of heads, and then they will just perform the same procedure and count how many outcomes have how many heads and assign the probabilities in the same way. Right, so now we have a random variable, which means we have numbers. So we can start performing some calculations. Now the first thing, before we get to the actual calculations, is just to introduce some new terminology. If we look at the list of x values and the associated probabilities, then we call this the probability mass function, or in other words, in short, the PMF. Now the PMF graphically looks like a histogram, right? Looks like a histogram. And in fact, this PMF, probability mass function, this table, looks almost like relative frequencies for samples, where we have the outcomes and we have our relative frequencies. What is a relative frequency? It is simply the frequency divided by the sample size. So what is this? It is the frequency divided by the population size. There's one outcome in the sample space that have no tails, and that's the 3 heads. There's 3 outcomes in the sample space that have 1 tail. So we're simply counting the number that we're interested in out of a total of the population size. So it's a lot like relative frequencies for samples. And as I just mentioned, this bar graph over here looks like a histogram for samples. But in this case, it'll be for a random variable, in other words, a population. Now next, if we look at combining or adding together the probabilities, then we call that the cumulative distribution function, or in short, the CDF. So when x is equal to 0, we've only accumulated a probability of 1 over 8. When x is equal to 1, we have accumulated 1 over 8 and 3 over 8, and that gives us 4 over 8, which is a half. When x is equal to 2, we've accumulated 3 over 8 and 1 over 8 and another 3 over 8, so that gives us 7 over 8. And then of course by the time we get to the end, we have accumulated everything. Right, so this is the same as what we had before for samples. It's like the ogive. Right, the column in the table where we looked at the frequency distributions, and the specific column was the cumulative relative frequencies. So that is similar to what we have here. Right, now the CDF graph is what we call a step function. Okay, this thing over here is a step function, and for obvious reasons, because it looks like steps. Now, if we look at what it represents, when we are at 0, then the probability that we've accumulated is 1 over 8. So at 0, the probability is 1 over 8. Now, when we get to 1, the probability becomes a half, because we're adding those two together, and a half is just 4 over 8, so it's there. So that means that from 0 all the way up to just before 1, the probability remains 1 over 8, and then at 1, it jumps up to become 4 over 8. Okay, so that's why I've got this empty circle over here, because there's no value over here for x equal to 1. Okay, the value is not 1 over 8. For x equal to 1, the value becomes 4 over 8. So the same over here. You can see that it stays 4 over 8 until we get to 2. Then it jumps, because at 2, we are adding another 3 over 8, so it becomes 7 over 8. So that's why it jumps up to here. And the same for the last one, where it jumps up to 1. Right, so our CDF for our discrete random variable is a step function. Now, in general, what we have is we simply have our outcomes, right? Our random variable x, which will be the outcomes represented from the sample space. We have the probabilities for each of those outcomes. So the probability of getting x1 will just be p of x1. Getting x2 will be p of x2, and this is just a short notation for this over here. Probability of x equal to a specific value. Right, this will be our PMF, and it's like the relative frequencies for samples. Properties that I've mentioned before for probabilities remain the same for random variable probabilities. It stays between 0 and 1, and when you add everything up for all possible values of x, that's what this symbol means, for all x, then the total will be equal to 1. And we did expect these results over here, right, these two properties, because it's exactly the same as those for the sample space where these probabilities come from. Right, then we have our CDF, or our cumulative distribution, which is like an ogive, where we simply add at every single step. Okay, so we just keep on adding. So start off with the probability for x1, then the first step, second step, it'll be x1 plus x2, third step, we'll add x3, and so we'll carry on. And the properties now for the CDF. Okay, first of all, it's denoted by a capital F, always a capital F for the CDF. If x is less than the smallest value in the sample space, or less than the smallest value of our random variable, then the probability will be 0. Because only once we reach the smallest value in the sample space, then we start accumulating. Before that, we have nothing. Once we've reached the largest x value and we pass it, then we have a probability of 1, because then we've accumulated everything. And if we want to find the probability of a specific value using our CDF, then we will take the probability of being at x, or less than or equal to x rather, and we'll subtract being less than or equal to x minus 1. So in other words, if I look at these two over here, if I'm interested in finding the probability of x2 and I'm given the CDF, okay, probability of x2, then I'll take that result and I'll subtract that one. Okay, so that's simply what this means. I'll take the CDF for x2, which is this, and I'll subtract the CDF for x1, so those two will cancel, and I'm left with the probability for x2. Alright, we'll have a look at this in a little bit more detail when we do the examples. Right, now very important, these functions, the PMF and the CDF, can be presented as a table or as an equation. And again, we'll have a look at some examples to illustrate this. Right, now regarding the distribution parameters, when we looked at samples, we calculated things like x bar and a squared. We called those sample statistics. They summarize the sample values and tell us something about the sample. For random variables or populations, we have parameters. And remember, parameters are always denoted by Greek letters. So that's exactly what we have in this case. The mean, which will be denoted by mu, is the expected value of x, and it is calculated in this way. Now all that this means is that we take each x value, we multiply it by its own probability, and we add all of those products together. If we want the variance, then it will be the expected value of x squared minus the mean squared. Now we've already calculated the mean over here, so we'll use this calculation. Whatever answer we get there, we'll square it, and we'll subtract it from this then. Now what is that? Well, expected value of x squared simply means that we'll take each x value and square it, and then multiply it by its probability, and then add everything together. Right? Add all those products together. Once you have that, you subtract the mean squared. And that's the variance calculation. Right, now just a reminder, these Greek letters, population parameters, and they also refer to random variables, right? Because a random variable refers to a population. Now let's have a look at the coin flip example I started with. If we look at calculating the mean, then what it says over here is we first need to take each x and multiply it by its probability. So that means we'll need another column over here, x times its probability. So the first result here will be 0 times 1 over 8, x, okay, this will be my x1, times its probability, so that will be the probability of x1, and that will give me 0. 0 times anything, of course, is 0. Right, in the next one, this will be my x1, and this will be the probability, sorry, this will be my x2, and this will be the probability of x2, so multiplying the x value by its probability, 1 times 3 over 8, we get 3 over 8, and if we do that for the other two, then this says that we have to add all those products together, and that will give us our expected value, in other words our mean. So adding all of this together, we have 3, 6, which is 9, plus 3 is 12, so it's 12 over 8. So in other words, if you want to write it as a decimal, then 1.5 tails are expected when flipping a coin 3 times. Now please note, we saw this when we worked with samples as well. Summary values, whether it's statistics or parameters, okay, summary values like means, medians, it is not necessarily a value in the data set. Right? It doesn't have to be a value in the sample or in the population. As you can see here, 1.5 is what we expect, but we don't have a 1.5. We have a 0, 1, 2, and 3. So all this is saying is that in the long run, the results is going to be between 1 and 2. Okay, so it's going to alternate between 1 and 2. Now what about calculating the variance? Well, for the variance, we need this thing over here. So that's why we bring in another column where we can calculate x squared times the probability of that specific x value. And we do exactly the same. We take the first x, remember this is my x1, so we square it, and then we multiply it by 1 over 8, so in this case it's 0. We take the second x value, which is 1, we square it times 3 over 8, that gives me just 3 over 8, and we do the same for the others, and we add them together. So this is my expected value of x squared, 24 over 8. Now what this says is that we need to take the 24 over 8, then we need to subtract the mean squared, and that will give us our variance. So the variance will be the 24 over 8 minus 12 over 8 squared. Okay, this 12 over 8 is the mean that we are squaring, so 12 over 8 squared. And this will give us a common denominator of 64, so 192 minus 144, if my calculation is correct. That will give us 48 over 64, in other words, 3 over 4. And if I want the standard deviation, then I'll simply take the square root of 3 over 4. Now that will be my standard deviation. Right, now the next bit looks at linear transformations. Now, linear transformations is a very important section, and in the next session there will be an example demonstrating that as well. Now let's consider 5 measurements, just any 5 that I randomly chose: 76, 72, 65, 70, and 82. Now taking those, and in this case I'll call them my population. Okay, they don't have to be, it can be a sample, but I'm just going to call it population for now. Graphically, on my number line, this is where they will be. So this will be my dot plot representing the population, and then if I calculate the expected value or the mean, it's going to be 73, and the standard deviation is going to be 6.4. And you can go back to the section on descriptive statistics to see how to calculate this, because that's where we saw it for the first time, but you can also go back a few slides because it is demonstrated there. Remember, standard deviation is just the square root of the variance. Right, now let's say for example that I take my x and I add 3 to every x value. Now if I do that, then I don't have an x anymore, or dataset x, so I'll call it dataset y1, because it changed now. So that means 76 becomes 79, 72 becomes 75, 65, 68, etc. Right, adding 3 every time. Now if I calculate the mean for y1, I see that it is 76. Okay, graphically this is what happened. Everything just shifted up by 3 units. So we see that the mean is equal to 76. The original mean for x was 73, but then I took 3 and I added to every single observation. So what do you notice? We notice that the mean for y1 is just the mean for x plus 3. In other words, whatever I did to the data, in other words adding 3, the same thing I can just do to the mean of x to get the mean for y. And we can see here the whole thing just shifted. What about the standard deviation? Well, standard deviation is the spread. If we look at what happened here graphically, the spread for the original x looks to be the same as the spread for y1. In other words, by adding 3, it didn't change the spread of the data set. And we can see that when we calculate the standard deviation of these values, it is 6.4, which is exactly equal to the standard deviation of x. Right, so adding did not change the standard deviation. In other words, the spread. So if the spread didn't change, it means that the standard deviation didn't change, the variance didn't change, and the range didn't change. Right? All of those are measures of spread. Even the interquartile range, that did not change as well. Right, now what about another situation? We will take the original x and we'll multiply it by 2. So that means my data set will now be 76 times 2, which is 152, 72 times 2, which is 144. Then we do the same for the rest. Graphically, this is what happened now. Now what do you notice? Well, the mean is a measure of spread. These values are definitely not in the same place anymore. So the mean must have changed. What do you notice about the spread of the data? Well, this is the original spread. But you can see here the spread is much, much wider. So it seems like by multiplying our random variable by something, we did not just change the location, because remember the mean is a measure of location, we also changed the spread. So let's see. If we calculate the mean for this data set, we get 146. And what do you notice? 146 is just 2 times the original mean. Right? 2 times the original mean. So in other words, I multiplied my data set by 2, so the mean is just multiplied by 2 as well. What about the standard deviation? Well, very interestingly, it's 12.8. And what do you notice about 12.8? It is nothing but 2 times sigma x. In other words, when I multiply my data with a value, then it seems like the mean is just multiplied by that value, and the standard deviation is also just multiplied by that value. Now lastly, what happens if we combine everything? If we take our original data set and we multiply it by 2 and then we add 3 to it. So now we're going to get 76 times 2 plus 3, which is 155, and do that for all the others. Graphically, this is what we have. So what do you notice? Again, the location changed and the spread changed. So let's see. The mean for y3 is 149. So how do we get to 149? Well, 149 is nothing but 2 times the original mean, right? 2 times 73 plus 3. So in other words, what I did to x over here, 2 times x plus 3, I'll do exactly the same to the mean to get the new mean of 149. What about the standard deviation? Well, interestingly, it's 12.8. We actually should have expected 12.8 because from this example here, we saw that adding something to the data did not change the standard deviation, but multiplying did change the standard deviation. So the addition of this 3 did not have any effect on the standard deviation, only multiplying. So that's why this one is still 12.8. Right, now over here it says sample. Now all that I'm assuming here is that this is a sample now. So what changed? Well, I'm not going to have mu anymore, I'm going to have x bar. I'm not going to have sigma anymore, I'm going to have s. And the reason is because for a sample we have statistics and we use normal alphabet to denote the statistics, where for parameters we have the Greek letters. Although the calculations will change, the results will stay exactly the same. In other words, whatever we do to x will be reflected in the same way as for the parameters. Right, so in general, to summarize that, if we have a random variable x and it has a mean mu x and it has a variance sigma x squared, and if a and b are 2 real constants, then the expected value of ax plus or minus b, okay, it doesn't matter whether we're adding or subtracting, will simply be a times the mean plus or minus b. So in other words, whatever we're doing to the x over here, we're multiplying it by a and we're adding or subtracting b, we do the same to the mean. we're multiplying by A and we're adding or subtracting B. For the variance, whatever we add or subtract will have no effect. You can see here, there's nothing there. We saw that from the example. But whatever we multiply, we have to square and multiply by the variance. Remember, in the example, we simply had 2x, so the variance, or rather the standard deviation, was 2 sigma. But the standard deviation is the square root, so when we take the square of that, then it means we're going to get a squared. Right, we can extend that result if we bring in another random variable y. And this one has a mean mu y and a variance sigma y squared. Now you'll see that I use subscripts x and subscript y, subscript x over here and subscript y over here. And the reason is because the subscript is an index. It tells us what random variable we're working with. Because we use the same letter, right, we use the same Greek letter mu for the mean, we need a subscript to distinguish between the random variables. And the same for sigma. Right, now, if we consider these two, okay, for x we have that, for y we have that, then the expected value of x plus or minus y, which is just the mean that we take for the calculation, x plus y or x minus y, will simply be the mean of x plus or minus the mean of y. And this is always the case. Okay, so the expected value of this calculation will be that calculation for the two expected values. Now this result we call the distributive property of. Now lastly, if we take the sum of our two random variables x and y and we calculate the variance, then it's going to be the same as taking the variance of x and adding the variance of y. Interestingly, if we take the difference between x and y and we calculate the variance of x and y, then this is also going to be equal to the variance of x plus the variance of y. So it doesn't matter whether we take x plus y or x minus y, we will add the two variances together. However, this is only true when x and y are independent. It is not true when they are dependent. So always check to see whether you are told that x and y are independent. If they are, then you can directly add the two variances together. Right, this is the end of the overview for random variables. In the next session, I will be looking at some examples.